Hi students, today I am going to explain some important bits especially from chemical kinetics. So in this, by considering some models, I am going to reveal the related concept which is going to be applicable for that particular question. So for that, suppose if you observe the first bit, see that is related to the rate of reaction. The rate of reaction is nothing but the change in concentration of either reactants or products per unit time. That is what we call as rate. And now imagine if you observe this question. Here they mention the equation like this. So that is 2a plus 3b gives rise to A2 B3. This is the equation, means reaction. Now, if rate of disappearance, of A is, that is nearly 2.5 into 10 power minus 3 mole per second. Then what is the rate of appearance of, not appearance, it is also disappearance. Then the rate of disappearance of B is, this is the question. Now see this, here as per this balanced equation, both A and B, they are reacting in 2:3 ratio. Means if 2 moles of A was disappeared, here 3 moles of B is going to be disappeared. So that is the meaning. Now if you observe the rate of disappearance of A, here for 2 moles, means as per the balanced equation, that is 2.5 into 10 power minus 3 mole per liter per second inverse. Now see here, generally in any reaction, either rate of appearance or the disappearance, whatever it may be, that formula you have to remember. So here rate of appearance or disappearance, this is equal to rate of the reaction into its stoichiometric coefficient. This is the formula what we have to remember. So now they mention the rate of disappearance of A. Now we have to find out rate of disappearance of B. So for that, here the formula, that is rate of reaction into stoichiometric coefficient. Now as per this, what is rate? Rate is nothing but rate of disappearance or appearance by stoichiometric coefficient. So according to this, rate equal to, since here they mentioned disappearance, I am considering rate of disappearance by stoichiometric coefficient of the particular substance. So now first we will go for rate. So that is nothing but, what is rate of disappearance of A here? That is 2.5 into 10 power minus 3. So 2.5 into 10 power minus 3 by its stoichiometric coefficient, that is 2. So this is rate. So therefore, rate of disappearance of B, that equal to rate into its stoichiometric coefficient. So that means 2.5 into 10 power minus 3 by 2, this is the rate, into its stoichiometric coefficient, means 3. So now if you observe this, here it is 7.5 by 2, or here it is 1.25, this is 1.25. So now into 3, so that is 3.75 into 10 power minus 3 mole per liter per second. So that is the rate of disappearance of B. So like this, in this model, it is a fundamental model related to the rate. So first of all, you have to remember this formula. Either rate of appearance or the disappearance. That is nothing but rate into stoichiometric quotient. As per that, rate equal to rate of disappearance or appearance by stoichiometric quotient. So it is very simple to analyze this type of models. For that, this is the standard relation what we have to remember. So this is one standard model. Means they are giving disappearance of one substance and they are asking disappearance of another. Or otherwise, they will give the disappearance of A and they will ask appearance of A to B3. So then the rate of appearance is nothing but rate into its stoichiometric quotient. So first observe that balanced equation, and by using those stoichiometric quotients, you have to find out the given concept. So this is one model. And next, another important one. Here, sometimes in terms of pressures, they used to give the bit. For that, here we have one important model, that is, for example, here the process is like this. A2, it is going to decompose to B plus half C. This is the process. Now, in this, the information what they are giving. Suppose in this gaseous phase reaction, if the pressure increased is from 100 to 120 mm in 5 minutes. So here in 5 minutes, pressure increased from 100 to 120 mm during that decomposition. Now, what is the rate of disappearance of A2? So now here we have to find out the rate of disappearance of A2. So here in this situation, what is then the rate of disappearance of A2 is, here since it is one mole, its rate of disappearance is nothing but rate of reaction. So like that, sometimes directly they used to ask what is rate of reaction. So for that purpose, just see here, in 5 minutes increase in pressure is 100 to 120. So now I am removing this. Imagine this is the process. So initial pressure is 100. Initial pressure is 100. Decrease in pressure, let it be X. Now if it is X, it will be X and it is X by 2. This is happening in 5 minutes. This is in 5 minutes. So after 5 minutes remaining 100 minus X, X and X by 2. Now what is the total? So total pressure after 5 minutes, that is, we have to add all these. 100 minus X plus X by 2. Of course it is going to be cancelled. So this will be 100 plus X by 2. But the total pressure after 5 minutes, that will be equal to 120. So this is 120. So therefore X by 2 equal to 20. As per that, X equal to 40 mm. Means in 5 minutes, the decrease in pressure of A is 40. But what is rate of disappearance? Decrease in pressure per minute. So therefore, rate or rate of disappearance, that is nothing but 40 by 5, which is 8 mm per minute. That is the answer. So here basically initial pressure is 100, after 5 minutes it became 120. As per that, here we are calculating the decrease in pressure of A in 5 minutes. So in 5 minutes the decrease in pressure is 40. So then in 1 minute, that is rate, as per that 40 by 5. But here most of the students, the way how they are going to analyze, time is 5 minutes. increase in pressure, that is from 100 to 120. So increase in pressure they used to consider as 20. So in 5 minutes, change in pressure is 20. Now in 1 minute, that is, they are going to calculate as 20 by 5. That is wrong. This is the way how we have to analyze this problem with respect to the pressures. So be clear about that. Initial, involved, remaining, and we have to equate to the total. As per that, in 5 minutes, what is the decrease in pressure? Then per minute, that is nothing but rate. So this is another important one. And next, one standard model based on that rate. Here, see, I will give standard model. See, imagine this is the question. Third one. Suppose if the process is like this, N2O5 gives rise to 2NO2 plus half O2. This is equation. So for this reaction, suppose if the rate of disappearance of N2 minus D N2O5 by dt, this is equal to K1 into N2O5. Similarly, dNO2 by dt, if it is equal to K2 into N2O5, and dO2 by dt, dO2 by dt, that is equal to K3 into N2O5. So like that, with respect to N2O5, they compared the disappearances and appearances. Now, what is the relation between? If it is like this, the relation between K1, K2 and K3 is, this is the question. So now, here also, just we have to use the concept what you applied in first bit, that is a disappearance equal rate into stoichiometric coefficient, or rate equal to disappearance or appearance by stoichiometric coefficient. That form we have to use. So for this, see the way how we have to approach. First of all, if you observe this one, with respect to this N2O5, here I am giving the solution. So that is minus d N2O5 by dt, that is equal to K1 into N2O5, or otherwise first we will consider as K. So here, as per this formula, the relation what we are getting, K equal to K1. Okay, and next, if you observe this expression, it is 2 moles. This is disappearance. So now we go for rate. So that means D, that means 1 by 2 into dNO2 by dt, that is equal to K into N2O5, because that is the rate. This is the rate with respect to N2O5, this is the rate with respect to NO2, but rate is equal. So as per this, therefore dNO2 by dt equal to, we can cross multiply, that is 2K into N2O5. Now see this, dNO2 by dt equal to 2K into N2O5. Now here if you observe, in place of that 2K, we have K2. So according to this, here 2K equal to K2. That is one relation. And similarly, rate with respect to this oxygen means 1 by 1 by 2 means 2 dO2 by dt, that is equal to K into N2O5. That is rate. Now as per this, dO2 by dt, that is equal to k by 2 into N2O5. Now according to this, just see here, we have K3. In place of K3, we have K by 2. So as per this, K by 2 equal to K3. So like this, we got K equal to K1. Similarly here 2K equal to K2 and K by 2 equal to K3. So now just see, this is one relation. As per that, what is K? K equal to K2 by 2. And here K equal to 2K3. So as per this, here we are getting K equal to K1, and according to this, K equal to K2 by 2, and here it is K equal to 2K3. Now if you compare those three values, now I am removing this. So finally we are getting K1, that is equal to K2 by 2, that is equal to 2K3. So in simple English, if you want to express, if you multiply with 2, now it will becomes 2K1 equal to K2, that equal to 4K3. This is the correct relation between K1, K2 and K3. So like this, with the help of the given information, we have to equate the rates. Then automatically you will get the relation with corresponding rate constant. Now, without doing all these things, directly we will get this expression. K1, K2 and K3. How? See K1, here it is 1 by 1. Here we have 2, K2 by 2. Here we have 1 by 2, 1 by stoichiometric coefficient. So 1 by 1 by 2 means 2K3. So whenever the question is like this, just with the help of the stoichiometric coefficient, we have to consider as the denominators of those stoichiometric coefficient, then fundamental relation we get. So the given rate constant by its stoichiometric coefficient. Enough. Simple. But here I showed how to get this relation. But at the time of examination, no need to spend this much of time. So simply the given rate constants by their stoichiometric coefficient. After that, to go for simplification. So this is another important model here. Okay, and next we'll go for one more important one. See, sometimes they are going to change the concentrations, and we have to find out the ratio between the initial and final rates. So for that purpose, see, this is the process. R equal to K into A power N and B power M. This is the rate expression. Now what they are doing, if concentration of A is doubled and B is reduced to half, means if concentration of A, if it is doubled and concentration of B was decreased to half, then what is the ratio between new rate to initial rate? Suppose new rate is R2, initial rate is R1. So then what is the ratio between R2 and R1? This is the question. So already they mentioned the rate expression. After that they are going to change the concentration like this. So before changing concentration, imagine R1, that is nothing but K into A power N into B power M. This is R1. Now what they did, concentration of A was doubled and the concentration of B was reduced to half. So in case of R2, it is K into, it was doubled, means 2 into A power N. since concentration was doubled. And here concentration of B was reduced to half, means into B by 2 power m. So now if you simplify this, it will becomes k into a power n into b power m into 2 power n by 2 power m. 2 power n by 2 power m. So now if you observe this, it is nothing but R1. So therefore R2 equal to R1 into 2 power n minus m. So therefore R2 by R1, that is nothing but 2 power n minus m. So this is the ratio between initial and final and initial rates. So that is one important model. So just you have to consider the changes, how the concentrations either doubled or tripled or reduced to half or reduced to 1/4. So like that here we have to consider. And here I will give one more model as the fifth bit. This is the rate expression. Suppose if volume of the vessel was reduced to 1/4. So if volume of the vessel, if it is decreased to 1/4 of its initial volume, then what is the ratio between the new rate to initial? Same concept. For that, in place of this n or m, or we can keep the same values. So now R1, that is nothing but k into a power n into b power m. Next, volume was decreased to 1/4. If volume decreased to 1/4, what will happen to the concentration? Concentration increased by 4 times. So now R2 equal to k into 4a power n into 4b power m. So it will be k into a power n into b power m into 4 power n into 4 power m, means here 4 power n plus m. Okay, so like that we have to consider, but it is R1. So therefore R2 equal to R1 into 4 into 4 power n plus m. So like this also we have to analyze the new rate when compared with initial rate. So like this, be clear about the change in concentrations of the substances or change in volume of the reaction vessel. Okay, and after that, as far as rate concerned, here temperature dependence. So if you observe the temperature dependence, as per Arrhenius equation, we have one formula, that is K equal to A into e power minus EA by RT. That is the temperature dependence. And now related to that, here there is one question, an important model. That means as the sixth one, if you observe, in this process A gives rise to B. Here K1, it will be given as 10 power 15 into e power minus 2000 by T. And after that second reaction, C gives rise to D. Here it is K2, which is nothing but 10 power 14 into e power minus 1000 by T. So if the rate constants are like that, at what temperature? At what temperature K1 will be equal to K2? Means we have to find out that temperature. So for that, just now as I have given the equation, here the condition is K1 should be K2. So now if K1 equal to K2, means we have to equate both, that is 10 power 15 into e power minus 2000 by t equal to 10 power 14 into e power minus 1000 by t. Now just I am going to rearrange this, means 10 power 15 by 10 power 14, that is equal to e power minus 1000 by t by e power minus 2000 by t. So 10 power 15 by 10 power 14 means 10. So as per this, here we can write 10 equal to, if you bring this, it will becomes plus. So plus 2000 minus 1000 means 1000. So here it will be equal to e power 1000 by t. So 10 equal to e power 1000 by t. As per this, log 10 equal to 1 by, here we are getting the constant 2.303 into, since we converted that e, base e to log value, here it will becomes 1000 by t. So now what is log 10? Log 10 is 1. So 1 equal to 1000 by 2.303 into t. So therefore t equal to 1000 by 2.303. So it is approximately 434.2 Kelvin. So if it is like that, almost at 434 Kelvin, both K1 and K2, they are going to be equal. So it is another important model. Just process of simplification is important here. So if you have that idea how to simplify, automatically it is not at all going to be difficult. Okay, and after that, see here there is one more important model related to this temperature dependence. That is, the question is like this: during the decomposition of N2O. So here N2O is going to decompose as N2 and O2. N2O, N2 and half O2. So in this process, K equal to, they mention as 5 into 10 power 11. 5 into 10 power 11 into e power minus 29,000 by T calorie, T. So if it is like that, then what is activation energy? We have to find out activation energy. So in that decomposition, K is mentioned as like this. But according to Arrhenius equation, K equal to A into e power minus EA by RT. That relation already we know that. Now, if we compare this expression to this, in place of A, means Arrhenius factor, we have 5 into 10 power 11. So, no need to think about this. So, in place of this term, here we have e power minus 29,000 by t. So, according to this, 29,000 by t equal to EA by RT. So, t is going to be cancelled. So therefore, EA equal to 29,000 into R. As the expression, if they mention, it will be like this. Suppose if it is in joules or in calories, joules means we have to multiply with 8.314. If it is in calories, you have to multiply with 2. So this is another important model related to the rate. So like this, as far as rate of reaction concerned, first rate of disappearance and appearance. After that, by using change in concentrations or the change in volumes, how to get the rate expression. And on temperature dependence, these are the important models as far as the concept of rate concerned. And in next class, we will go for the important models related to order of the reaction. So before that, try to analyze these points in view of that objective examinations. Thank you.